Hello everyone, this is part 8 of Econometrics where we're going to talk about variance of estimators. So in the previous video, we went over some math that proves that our estimator for beta 1 is unbiased and consistent under our assumptions. So we passed the 2 statistical tests for our estimators to be reliable. In this video, we're going to go over a third statistical property, which is the variance of the estimators. Needless to say, we want our estimators, especially beta 1 hat, to have a small variance. This is because if assumptions hold, it would mean that with smaller variance, our estimate is more likely to be closer to the causal effect. And now we're going to be computing for variances. And in order to start computing for variances, we need to add a couple of assumptions here. So first, note that we had these 4 assumptions, and these are the ones that you saw already. Here, since we're talking about assumptions, I want to make a quick note that in addition to the model being linear in parameters, since y is the exam score and x is the hours studied in our example, by specifying a model like this, we're also assuming that exam scores and hours studied follow a linear relationship. I already mentioned this in part 1 video, and I said that since we don't want to overcomplicate things, we'll just assume for now that exam scores and hours studied follow a linear relationship. So what I'm trying to say is, if you want to be really meticulous, you can add here that by specifying a model like this, we're assuming that y and x have a linear relationship, whatever y and x may be. Okay, so then these are the assumptions that we had so far, and now I'm going to add these 2 assumptions at the bottom. Later on, we can relax or modify these 2 assumptions at the bottom, but for now, we're going to keep these 2 assumptions to start with. So assumption number 5 is saying that variance of ui given xi is sigma squared. So by now, I hope you already noticed that I used the words given and conditioned interchangeably. So they mean the same thing. Okay, so coming back here, note that sigma squared doesn't have an I subscript, so the condition of variance is the same for all UIs. Now, assumption number 6 is saying that condition on xi, ui is going to be distributed normal with mean 0 and sigma squared. So the new information in assumption number 6 is that the conditional distribution of ui follows a normal distribution. The 0 conditional mean we already assumed from assumption number 3, and the variance we already assumed from assumption number 5, right? So the new information is the normal distribution here. And of course, these assumptions are for I equals 1 through n. So with these 2 assumptions, we now have some other results. First, we already know that expected value of yi given any value of xi is beta 0 plus beta 1 times xi. And this is because of our third assumption. Now, variance of yi given xi is simply going to be sigma squared because of the fact that beta 0 plus beta 1 times xi is non-random, and also because of our 5th assumption. If we combine the results here, then by our 6th assumption, we know that yi given xi is going to follow a normal distribution with its mean and variance. And so condition on xi, the distribution of yi is going to be exactly this under our assumptions. So how does all of this look like on a graph? Well, you already saw it, and it looks like this. You should note that here, the reason I'm showing the graph for the population is because, like I mentioned before, we can generalize the assumptions to the population since we're assuming a random sample. And our assumption number 5 is now telling us that the variance is going to be the same given any value of xi. So if you eyeball the graph a little bit, you can see the dispersion of errors. For instance, the dispersion given x equals 2 and dispersion, for example, given 6 hours of studying should be about the same. And they look the same, right? And it's going to be the same regardless of which hours of studying that we're conditioning on. So dispersion of error or dispersion of y given any x value is going to be the same. That's what our 5th assumption is telling us. For the 6th assumption, it's hard to see on the graph here, but condition on any x value, the errors are going to be normally distributed. So to better see what's going on, let's think about the situation where we condition on x equals 2. If we take all the errors when x equals 2 and come up with the distribution, then we're going to get a distribution that looks like this. This is a normal distribution with mean 0 and variance sigma squared. So according to our 6th assumption, many of the errors are going to be near the center or near 0, and we're going to have fewer errors as we get further away from the center. And this is going to be the distribution not just for x equals 2, but any value of x. We also know that yi, or exam scores, are normally distributed given 2 hours of studying, or given any x value in general. According to our assumption, the exam scores are going to be normally distributed with mean that equals beta 0 plus beta 1 times xi. So the mean of the distribution would change depending on x value, obviously, but the variance of this conditional distribution remains the same. And as we calculated already, that condition of variance is simply sigma squared, the same condition of variance for the errors. Okay, now that we went over the assumptions, let's find the variance of our estimator. I'm going to focus on beta 1 hat since that's our estimator of interest. So we know by now that beta 1 hat is expressed using this equation, which then means that the variance of beta 1 hat conditioned on some sample values of x is going to be expressed using the equation in the second line. Since beta 1 is constant or non-random, we can ignore it so that we get this term for the conditional variance. Now, if we focus first on the denominator, that term in the denominator is non-random, so we can take it out of the variance operator like this. And of course, we have to square it when we take it out. Now, I'm going to pull up the equation at the bottom to the top, and I'm going to expand the summation in the numerator. Note that condition on x values, all the terms with x are non-random. Also, since ui's are IID by our first assumption, the variance of the sum here is going to be sum of the variances, so that we're going to end up with this term. Now I'm going to condense it down using summation so that we end up with this term at the bottom, which I'm going to pull up to the top now. From here, again, because of IID assumption, this term becomes this term since ui has nothing to do with other xi's except for xi itself. Now, we can apply our fifth assumption in this term so that we end up with this term. Note that sigma squared does not have an I subscript, so it's simply going to be some constant value, which means that we can cancel some terms in the numerator and the denominator. After canceling terms, we finally arrive at a solution which says that variance of beta 1 hat conditioned on some specific x values is equal to sigma squared divided by that term in the denominator. Alright, so then with this conditional variance, we now know the distribution of beta 1 hat. Using this equation, we can see that condition on some x values, beta 1 hat is going to follow a normal distribution as long as ui given some x values follow a normal distribution. Note that by our IID assumption, this conditional distribution is the same as this conditional distribution, and this distribution is ensured by our sixth assumption. So all of this means that beta 1 hat conditioned on some x values is going to follow a normal distribution with its mean and variance, which we now know is this at the bottom, as long as our assumptions hold. Okay, then graphically, how does all of this look like? Well, it's going to look like this. So this is showing the distribution of beta 1 hat given some x values. What does this graph mean intuitively? Well, given a random sample, we're going to have some specific value of x1 through xn, which are ours studied in our example. We're also going to have n number of exam scores. Using this data, we compute beta 1 hat. Now, suppose we can get a different set of exam scores using the same set of x values ours studied. We compute another beta 1 hat. Continue the process until we have a very large number of beta 1 hats. If we plot those large number of beta 1 hats using histogram, it's going to look like the graph on this page. So that's what's going on. Okay, then let's take our sample as an example. Using the 30 data points, we calculated beta 1 hat to be 0.048. So if the graph here represents the distribution of beta 1 hat conditioned on the 30x values from our sample, then 0.048 definitely belongs in this distribution somewhere. The problem is, we don't know where 0.048 lies in this graph. 0.048 could be here, close to the beta 1, the cause and effect, or it could be somewhere here far away from beta 1. But what we do know for sure is that the smaller the conditional variance, the more likely beta 1 hat, or 0.048 in our example, is going to be close to beta 1. So the bottom line here is that we want the conditional variance to be as small as possible. At this point, some of you may be wondering if it's okay to use the variance condition on some fixed x values. Well, without getting into too much detail, for now, the straight answer is yes. We actually have a formula for the unconditional variance, which is this. But the problem is we cannot calculate this term because we don't know the distribution of xi. But that's okay because, like I said, for a couple of reasons, using the conditional variance is going to turn out to be okay. As an example, using the conditional variance, later on you're going to be calculating some other statistics, such as t-statistic, confidence interval, and p-value. And t-distribution, which is the basis of all of these statistics, at the end will turn out not to depend on any specific x values. If you're not understanding what I'm saying at the moment, that's okay. Just know that it's okay to use the conditional variance. Alright, the next question in this video is how do we calculate the conditional variance? The problem is we don't know what sigma squared is, the variance of the error term. So what we're going to do is we're going to estimate it using this equation. So then, for example, given a particular sample, we can come up with an estimate, a particular number for conditional variance for beta 1 hat. Now, I want to make some final comments about our conditional variance. Note that all else equal, with larger variance of ui, the conditional variance is going to be larger. And also with smaller dispersion of xi, the conditional variance is also going to be larger. And I'm going to leave it up to you to pick your brains and think about why that's the case intuitively. It's also important to note that all else equal, as sample size or n becomes larger, the denominator in the conditional variance becomes larger, which means that the conditional variance becomes smaller. Eventually, with n large enough, conditional variance converges to 0. This is good because it means that in general, as long as assumptions hold to be true, the estimator returns more precise estimates as n becomes larger. This means that if you have a small sample size, for instance 30 data points in our example, then even if you believe the estimator is unbiased and consistent, the estimator may still be unreliable because with larger conditional variance, you are less going to be confident that your estimate for beta 1 is going to be close to the true value, the causal effect of our studied on exam scores.